The integral test and the comparison test both have the hypotheses that the terms of our series have to be positive. But there's a lot of important series that we want to know about that don't have all positive terms. For example, we have the series -1 to the n over 2n plus 1. We define an alternating series as any series where the terms alternate sign. Depending on whether we want the odd terms to be positive or the even terms to be positive, we'll have -1 raised to either the n minus 1 or the nth power. Occasionally, since sine and cosine alternate every pi or pi over 2 interval, we could also use trig. So when we have a series of the form -1 to the n minus 1 times b sub n, that simplifies down to b sub 1 minus b sub 2 plus b sub 3 minus b sub 4, and the pattern continues. So b sub n is always greater than 0. That gives us the size of the terms, while the -1 to the n minus 1 gives us the sign of the terms. Just a quick note on the notation. B sub n is the 1 over 2 to the n plus 1. And consistent with how we've been defining series up to this point, a sub n would be the entire thing to the right of the summation notation. So it would be -1 raised to the nth power over 2n plus 1. The alternating series test tells us that if the limit as n approaches infinity of b sub n is equal to 0, and 0 is less than b sub n plus 1, less than b sub n for all n, and really all that means, it's math speak for saying the size of the terms of our series are decreasing. And it doesn't have to be for all n, it just has to be for all n greater than or equal to some number. As long as the size of the terms start decreasing and continue decreasing at some point, then we're good. And then by the alternating series test, that tells us that our alternating series converges. What about an alternating series makes this work? We need to fall back on our limit of partial sums. We know that s sub 1 is b sub 1, just the first term in our series. S sub 2 is b sub 1 plus a negative b sub 2, or b sub 1 minus b sub 2. S sub 3 is the sum of the first three terms, but S sub 3 is equal to b sub 1 minus b sub 2 plus b sub 3, and b sub 1 minus b sub 2 is s sub 2. So we could rewrite this as s sub 2 plus b sub 3. For s sub 4, the sum of the first four terms is equal to s sub 3 minus b sub 4. In this shortcut method, this pattern continues. S sub 5 is equal to s sub 4 plus b sub 5. S sub 6 is equal to s sub 5 minus b sub 6. Let's look at this geometrically. We start at 0, and the first term of our series is b sub 1. So we add b sub 1, and that gives us s sub 1. To find s sub 2, we start with s sub 1, and we subtract b sub 2. Adding b sub 3 to s sub 2 gives us s sub 3. To find the next partial sum, we add the next term, which is a negative b sub 4, giving us s sub 4. We add the next term, a positive b sub 5, giving us s sub 5. The next term in our series would be a negative b sub 6, giving us s sub 6. Each partial sum is nested between the previous two terms because the terms are decreasing in size. Since the limit as n approaches infinity of b sub n is 0, then we know the width of these intervals is getting smaller and smaller. Eventually, it'll approach 0. That tells us that the limit as n goes to infinity of our partial sums, our s sub k, is going to approach some finite number. And not only is it going to approach some finite number, that number is going to fall somewhere within the last two partial sums that you find. So in this case, we know that the sum of the series is going to fall somewhere in between whatever the values of s sub 5 and s sub 6 are. That means that the alternating series must converge. Let's do an example. This is the same series from our previous page. Notice here that we're starting at n equal to 0 to infinity of negative 1 to the n over 2n plus 1. The negative 1 to the nth power makes this an alternating series, where our b sub n is the size of the terms, 1 over 2n plus 1. We need two things to be true before we can apply the alternating series theorem. First, we need the limit as n approaches infinity of 1 over 2n plus 1 to equal 0. And in this case, that is clearly true because the numerator is 1, the denominator is growing without bound. There's really no work to be shown here. The second part, we need our terms to be decreasing. So let's start by defining b sub n plus 1. We already know from above that b sub n is equal to 1 over 2n plus 1. So to find b sub n plus 1, we just want to replace n with an n plus 1, giving us 1 over 2 times n plus 1 plus 1. In order for our terms to be positive and decreasing, we need 0 less than b sub n plus 1, which is 1 over 2 times n plus 1 plus 1, less than 1 over 2n plus 1. This is true if and only if 0 is less than 1 over, simplifying in the denominator, we have 2n plus 2 plus 1, which is 2n plus 3, less than 1 over 2n plus 1. And this is true if and only if taking the reciprocal of both sides gives us 2n plus 3, and we flip the inequality sign because we took the reciprocal, greater than 2n plus 1. And the 2n's on both sides cancel out, so this is true if and only if 3 is greater than 1. This is clearly true. And so we can say that 0 is less than b sub n plus 1 less than b sub n. Quick side note here. Only refer to your terms as b sub n and b sub n plus 1 if you've explicitly defined them somewhere previously on the page. So because we had already defined our b sub n as 1 over 2n plus 1 and our b sub n plus 1 as 1 over 2n plus 1 plus 1, we can later refer to it here as b sub n plus 1 and b sub n. We don't have to write it out longhand again. Always give your conclusion in that since-then form. Since the limit as n approaches infinity of 1 over 2n plus 1 is equal to 0, and 0 is less than 1 over 2 times n plus 1, which is less than 1 over 2n plus 1 for all n greater than or equal to 1. And at this point, I'm going to sneak back up. I realized I left that off earlier. I'll add that in. Then our alternating series converges. And naming our test by the alternating series test. And it's fine if you abbreviate alternating as ALT. The alternating series test only tells us that the series converges. But in fact, this series from n equals 1 to infinity of negative 1 to the n over 2n plus 1 is equal to arctan of 1, which is pi over 4. But we're going to have to wait a few more sections until we figure out exactly why that works. Let's try another example. Here we have this series, negative 1 to the n minus 1 times n over n plus 1. We want to know if it converges or diverges, but we're not told what test we should use. Fortunately for us, the alternating series test usually stands out for us because of the alternating terms. I'll define our b sub n so we can later refer to our terms as just b sub n instead of having to write out n over n plus 1. So we'll start with the alternating series test. Our first argument, we need to prove that the limit as n approaches infinity of n over n plus 1 is equal to 0. Now, as this limit is written, it's indeterminate. We have that infinity over infinity form. Anytime you're trying to evaluate a polynomial over a polynomial, the easiest way to evaluate that limit is to multiply by 1 over the highest power term in the denominator. So let's multiply the numerator and the denominator by 1 over n. That gives us the limit as n approaches infinity of 1 over 1 plus 1 over n. And as n goes to infinity, 1 over n goes to 0, giving us 1 over 1 plus 0, which is 1, and 1 is not equal to 0. Now, we have not satisfied the hypotheses of the alternating series test, and the alternating series test does not prove divergence. It only shows us whether a series converges. That means if we haven't satisfied the hypotheses of the alternating series test, that series could converge or diverge. There's not enough information and we don't know. We need to find another test to tell us whether the series converges or diverges. But now we know that this limit is not equal to 0. And so the divergence test tells us that our series from n equals 1 to infinity of negative 1 to the n minus 1 times n over n plus 1 diverges since the limit as n approaches infinity of negative 1 to the n minus 1 times n over n plus 1 is not equal to 0. If the limit as n approaches infinity of b sub n is 1, then the limit as n approaches infinity of negative 1 to the n minus 1 times b sub n is going to alternate between negative 1 and positive 1, which does not exist, and that's still not 0. This is a nice general case of when the alternating series test fails. You'll often find that the only reason it will fail is because the limit will not equal 0, and so then you can fall back on the divergence test to prove divergence. Here we have the alternating series -1 to the n minus 1 times n plus 3 over 2n squared plus 4. And we want to show it converges using the alternating series test. I've started the outline of our arguments for us just to save us a little bit of time. Whenever you are trying to evaluate the limit as n approaches infinity of some polynomial over a polynomial, that rational function, we want to multiply by 1 over the highest power term in the denominator. So here, let's multiply both the numerator and the denominator by 1 over n squared. This is equal to the limit as n approaches infinity. In the numerator, we have 1 over n plus 3 over n squared. And in the denominator, we have 2 plus 4 over n squared. And this simplifies to 0 plus 0 in the numerator over 2 plus 0 in the denominator, which simplifies down to 0 as desired. We need our terms to be positive and decreasing. So our b sub n plus 1 is n plus 1 plus 3 over 2 times n plus 1, quantity squared, plus 4, less than b sub n, which is n plus 3 over 2n squared plus 4. This is true if and only if. Let's cross multiply and we'll simplify as we go. So on the left-hand side, the n plus 1 plus 3, that simplifies down to n plus 4. And cross multiplying, we bring the 2n squared plus 4 over to the left-hand side. And this is less than n plus 3 times foiling the n plus 1 and distributing that 2 out front gives us 2n squared plus our middle term when we are foiling out n plus 1 is 2n, and multiplying that by the 2 out front gives us a 4n plus 1 squared times 2 is 2 plus 4 gives us plus 6. Simplifying, on the left-hand side, when we FOIL that, we have n times 2n squared, which is 2n cubed, plus 4 times 2n squared gives us 8n squared, plus n times 4 is 4n, plus 4 times 4, which is 16. And that is less than, on the right-hand side, we have n times 2n squared, that gives us 2n cubed. N times 4n is a positive 4n squared, plus 6n. And now distributing the 3, we have plus 6n squared, plus 12n, plus 18. And I'll put my if and only if out front. For our next step, when you see this type of problem, bring all of your constants to the left-hand side and everything with a variable to the right-hand side. We have a 2n cubed and a 2n cubed, so those cancel out. Let's look at our squared terms. On the right-hand side, 4n squared plus 6n squared is 10n squared, and subtracting 8n squared from both sides gives us 2n squared on the right-hand side. Looking at our terms with an n, we have 6n plus 12n, which is 18n, minus 4n gives us plus 14n, and for our constants, we have 16 minus 18, giving us a negative 2 on the left-hand side. And this is an if and only if statement. Now, we know that n starts at 1 and is going to always be a positive integer. And so 2n squared plus 14n is always going to be greater than 0, which means it will always be greater than negative 2, and that will be true for all n greater than or equal to 1. For our conclusion, using our since-then statement, we have since the limit as n approaches infinity of n plus 3 over 2n squared plus 4 is equal to 0, and since I didn't define our b sub n or b sub n plus 1 anywhere on the page, I will write them out longhand. We have 0 is less than n plus 1 plus 3 over 2 times n plus 1 squared plus 4 less than n plus 3 over 2n squared plus 4. And this is true for all n greater than or equal to 1. Then our alternating series from n equals 1 to infinity of negative 1 to the n minus 1 times n plus 3 over 2n squared plus 4 converges by the alternating series test. In this example, it was a little more challenging to prove that our terms were decreasing. So you saw an example where we cross-multiplied, and then a nice, easy way to show that the inequality is true. Let's look at another example where showing the terms are decreasing is going to be a little bit more challenging. We have this series negative 1 to the n minus 1 times the natural log of n over n. This is alternating, so we'll start with the alternating series test. And let's define b sub n as the natural log of n over n. We need to prove two things. The first, that the limit as n approaches infinity of the natural log of n over n is equal to 0. But now as n is going to infinity, we have it in this indeterminate form of infinity over infinity. But we can't use L'Hopital's rule because L'Hopital's rule requires us to take the derivative, and we can only take the derivative of functions that are continuous. So instead, we need to let f of x equal the natural log of x over x such that f of n is equal to b sub n. Then the limit as x approaches infinity of the natural log of x over x is in that indeterminate infinity over infinity form. And so, using L'Hopital's rule, this is equal to the limit as x approaches infinity. The derivative of the numerator, natural log x, is 1 over x, and the derivative of the denominator is 1. And so now as x is going to infinity, 1 over x is going to 0. That tells us that the limit as n approaches infinity of the natural log of n over n is equal to 0. So we've satisfied the first condition of the alternating series test. Now we need to show that our terms are positive and decreasing. Plugging in our values for b sub n plus 1 and b sub n, we have 0 is less than the natural log of n plus 1 over n plus 1 less than the natural log of n over n. Cross-multiplying, we can say this is true if and only if n times the natural log of n plus 1 is less than n plus 1 times the natural log of n. Is this true? I'm not sure. Maybe if we used our natural log rules, we could rewrite this as the natural log of n plus 1 to the nth power less than the natural log of n to the n plus 1 power. Still not sure if that's true. We could keep trying to simplify and say that this is true if and only if n plus 1 to the nth is less than n raised to the nth plus 1. And again, it's just not obvious. We're not getting anywhere with this approach. So let's try something different. To evaluate the limit, we had already defined f of x as the natural log of x over x. And we know from the integral test that we can prove that f of x is decreasing by taking its first derivative and looking to see if it's positive or negative. So the derivative of f of x, using our quotient rule, we have low d high minus high d low all over the square of low we go. And that simplifies to 1 minus the natural log of x over x squared. 1 minus the natural log of x over x squared will be less than 0 when 1 minus the natural log of x is less than 0, since the denominator x squared will always be positive for all x. And adding the natural log of x to both sides, we have the natural log of x greater than 1. And solving for x, we get that x is greater than e to the first power, which is about 2.718. Let's put that all together then. F prime of x is less than 0 tells us that f of x is decreasing, which tells us that 0 is less than the natural log of n plus 1 over n plus 1, less than the natural log of n over n. And this is true for all n greater than or equal to 3, knowing that n has to be an integer. I'll give my conclusion at the top since I'm running out of room here. Since the limit as n approaches infinity of the natural log of n over n is equal to 0, and 0 is less than the natural log of n plus 1 over n plus 1, which is less than the natural log of n over n for all n greater than or equal to 3, then the sum from 1 to infinity of negative 1 to the n minus 1 times the natural log of n over n converges by the alternating series test. So in this example, showing that the terms are decreasing by cross-multiplying did not work for us. So if that doesn't work, then you can always create a corresponding function f of x such that f of n is b sub n, and then take the derivative of f of x to show that the derivative is negative, and so the function f of x is decreasing, and so the terms of the series have to be decreasing as well. While we can't find the actual sum of an alternating series, at least not yet, we can approximate the sum of an alternating series, and we can tell how accurate that approximation is. So far, only the limit of partial sums and the geometric series test actually tell us what the sum of a convergent series is. Since the terms of a convergent series have to approach 0 in order for it to even have any chance of converging, that means that the early terms are more significant to the overall value of the sum than the smaller later terms. And so we can use this to approximate an alternating series with at least some degree of accuracy using partial sums. Now, bear with me, the notation on this can be very confusing, but to actually apply it is very simple. When we have the infinite series from n equals 1 to infinity, we can break that up into two series. The sum from n equals 1 to capital N, plus everything that comes after. So we'd be starting at n plus 1, and we'd be going to infinity. These are the end terms, so they're going to be the ones that are closer to 0. The sum of the first n terms of a series, that's our partial sum. And since we're using a capital N here instead of a K, we're going to call that S sub n. This is our partial sum. And then all the remaining terms after that are what we call R sub n, where R sub n is the remaining terms after the first capital N terms. In other words, that's our error. So we're approximating the infinite series with the sum of the first n terms, S sub n, and what we're leaving off is R sub n, which is why we call that the error. But just how good of an approximation is this? Well, we can't find the exact error when approximating a convergent series with a partial sum. And here we have this little caveat that the only way we could find the actual error is if we knew what the actual sum was. And there are a few cases, as we'd mentioned earlier, such as arctan of x and the natural log of x, that we can approximate using our series later on. But for now, all that we can do is put a bound on the error. And that's because this is an alternating series. We call this the alternating series estimation theorem, which is a lot to write out. So you can just abbreviate it as ASET. And I will forever know that you're talking about the alternating series estimation theorem. We're given an alternating series, and the limit as n goes to infinity of b sub n is 0, and the terms are positive and decreasing for all n greater than or equal to some number. So all that means is that the alternating series has to converge. So given that you have a converging alternating series, then we're going to call S the sum of the entire infinite series. The absolute value of R sub n, that is the size of the error. And we use those absolute value signs because it could be an overestimate or an underestimate. And that is equal to the difference between the actual sum of the infinite series and the partial sum. And here's the nice part. This is always going to be less than or equal to the size of the next term. In other words, the next term is going to be the first term not used in the approximation. So big picture, if we have an alternating series and it converges, we can approximate it using the sum of the first n terms of the series, and we will know that the size of the error is going to be less than or equal to the size of the next term. Let's look at this geometrically to figure out why this works. Here, we're still going to use that same infinite series, the one that we know converges to arctan of 1. And we're going to approximate it with S sub 3. We want to use the alternating series estimation theorem. We know that our sum from 0 to infinity of negative 1 to the n over 2n plus 1 meets the hypotheses of the alternating series estimation theorem because back in example 1, we showed that this converges. Once we satisfy the hypotheses, then we know that the size of the error is going to be less than or equal to the size of the next term. So we're approximating the infinite series with S sub 3. So the next term after that is going to be B sub 4. Looking back at our series, we know that B sub n is 1 over 2n plus 1. So B sub 4 is 1 over 2 times 4 plus 1, which is 1/9. And that's all the work you have to show. We could rephrase this question as find a bound for the absolute value of the sum, the infinite sum, minus the sum from n equals 0 to 3 of -1 to the n over 2n plus 1. And now notice that we call this S sub 3, but there's 4 terms because we're starting at n equals 0. So just a quick reminder, notation-wise, that S sub 3 is not the number of terms, but the n value where you stop adding. So this infinite sum is S, and from n equals 0 to 3, that is S sub 3. Or we could ask to find a bound for the absolute value of the sum from n equals 4 to infinity, and this is R sub 3. I want to mention one more thing before we move on. What if the problem instead had said find a bound for the error correct to, let's say, 4 decimals? How would that affect our answer? 1/9 is equal to 0.111111, and it continues. So if we want 4 decimal places, that would be the first 4 ones here. But now, should we round up or should we round down? To answer that, let's think in the most drastic terms possible. The most we could round down is to 0. So let's just say we round down to 0. Then could you guarantee 100% without any doubt that the error is going to be less than or equal to 0? No, you can't do that because clearly we see the error is going to be at least 0.11 something. But now let's round up. Let's round way up. So let's say we round up to 1. Then could you guarantee that the error is going to be less than or equal to 1? Well, knowing that it's going to be less than or equal to 1/9, that seems like a sure thing. So we should feel really comfortable saying, yeah, I guarantee, let's round up. The error is going to be less than or equal to 1/9. So when you're finding error bounds, you always round up. In this case, if we wanted our error bound to be correct to 4 decimal places, then we would say the size of the error will be less than 0.1112, correct to 4 decimals. In workshop tomorrow and also in your homework, both of those questions are going to be worded in such a way that you will have to find the error bound correct to some number of decimal places. So you will need to know that you should always round up. Still dealing with the same alternating series, we want to know what is the smallest value of n needed to guarantee that S sub n approximates our infinite sum with the size of the error less than 10 to the negative 3. This is a converging alternating series, same from example 1, so we've satisfied the hypotheses. And we want the error to be less than or equal to 10 to the negative 3. And I always start these problems the exact same way. And that's by writing the size of the error is less than or equal to the size of the next term. The next term is going to be b sub n plus 1. And we want that to be less than or equal to 10 to the negative 3. This is the part of the inequality that we want to focus on. The size of the next term is 1 over 2 to the n plus 1 plus 1, which we want to be less than or equal to 10 to the negative 3. To solve this inequality, let's take the reciprocal of both sides. On the left-hand side, we can simplify that as we go, giving us 2 times n plus 2 plus 1, which is 3. Because we took the reciprocal, we swapped the sign of our inequality. And so that's greater than or equal to 10 cubed. And 10 cubed is 1,000. Subtracting 3 from both sides and dividing by 2, we have that n is greater than or equal to 1,000 minus 3, and that simplifies to 498.5. Now, n has to be an integer, and we're looking for the smallest n. So you shouldn't give your answer as an inequality. It should always be of the form n equal to. You always round up. So it would be n equal to 499. Now, in this example, algebraically, we should round up because when you have 5 or greater, you round up. But even if that had been 498.01, you would still round that up to 499. In this example, we were lucky because we could easily solve for n algebraically, but that's not always the case. So let's do an example where you can't solve for n algebraically. A lot of times when you're using the alternating series estimation theorem, I'll go ahead and just tell you that your series satisfies the hypotheses of the alternating series estimation theorem. And if that's the case, then you don't have to do any work. But if you're not told that, then make sure you do satisfy those hypotheses before you apply the alternating series estimation theorem. So we want to know how many terms do we need to approximate our sum with the size of an error less than or equal to 10 to the negative 6. We know the size of the error is going to be less than or equal to the size of the next term. So the next term, everywhere we see an n, we're subbing in n plus 1, giving us the inequality n plus 1 over 5 to the n plus 1 less than or equal to 10 to the negative 6th. So since we can't solve this algebraically, we want to use this method that we call guess and check. And I make a little table because I think it's easier to keep track of what's going on this way. So when n is equal to 8, then we sub 8 into this inequality, giving us 9 over 5 to the 9th. And that simplifies down to 4.6 times 10 to the negative 6th. This is the size of our error, and we want it to be less than 10 to the negative 6th. But 4.6 here is clearly greater than 1. And so our error is still too big when n is equal to 8. When n is equal to 9, then the next term after that, the first one that we're not using in the approximation, would be 10 over 5 to the 10th. And that simplifies to 1.024 times 10 to the negative 6th. And 1.024 is still clearly bigger than 1, which means that our error would still be too big. Let's try n equal to 10. Then, if we're approximating our infinite sum with the first 10 terms, the first term that we're not using would be 11 over 5 to the 11th. And that's approximately 2.25 times 10 to the negative 7th, Or if it's easier, you could think of this as 0.225 times 10 to the negative sixth. And that is clearly going to be less than 1, which means that our error will be small enough. In other words, if we use S sub 10 to approximate our infinite series, then not only will the size of the error be less than 10 to the negative sixth, we know the size of the error will be less than 2.25 times 10 to the negative seventh. When you're using this guess and check method to find your smallest n, you need to show two lines in your table. So for the minimum amount of work to show, you would need the first line where n is too big and the first line where n is small enough. So for full credit, you have to include those two lines. You can include more if you want, but you don't have to include the entire table. Now for your homework, for web work, I'd recommend use a graphing calculator or some other device so that you're not subbing this in by hand. Using the table function on one of your graphing calculators is generally the easiest way to do this. If it were an exam, then the numbers would work out so nicely that you could use a scientific calculator or even just doing them by hand.